Hi, I'm Oliver Gao. I'm the director of Cornell Systems Engineering Program, and we have been conducting what I call these systems conversations with our great speakers that we bring to Cornell to share their wisdom with us. So today we are very honored and delighted to have Dr. Brian Denton, who is actually the chair of the Department of Industrial and Operations Engineering at the University of Michigan. And his research interests are in data-driven sequential decision-making and optimization under uncertainty with applications to medicine, which is so important to our daily life. So, Brian, welcome to our conversation.
Yeah, thank you, Oliver.
Yeah, and I was looking at your experience. I saw you got your degrees in chemistry and physics as undergraduate, and now you are in the management science, and you are managing actually with medicine. This is really quite a cross, and apparently it's such a nice example of a systems, right, kind of evolution. Even your career path, and of course now your research. I believe including me and our audience, would love to hear more about yourself, your career, whatever you want to tell us about you.
Yeah, well, you pointed out I did my undergraduate degree in chemistry. I actually started in chemistry, and I was sure I was going to be a chemist. And then I discovered I wasn't very good at laboratory work. So I moved into physics, and I kept the chemistry part, so I did a chemistry physics double major. But I found I liked the math and the problem solving, more on the theory side in physics, because I was better at that than working in the lab, even though I wanted to be good at working in the lab. So that was the change for me. And then I did a master's in physics, also on the theory side. And then I started to wonder, what am I going to do after this? So I was thinking about a PhD in physics, but I heard about this field of operations research and management science, and decided to make what I felt was a enormous and somewhat stressful move to another area after what I think was a fairly small amount of research on it. So I started a PhD in that area, and that turned out to be one of the best decisions, I think, of my life. I took some of what I learned, so I don't consider my physics background to be a waste of time. I learned a lot about critical thinking and problem solving. I think was excellent preparation for me. But I love working in the field of operations research because there's so many different things you can do, and have some real societal impact, and just the diversity of opportunities. So when I finished, I started working at IBM. I went on the job market, and I knew I did not want to be a professor. That was clear to me. I didn't want to be a professor. I had a very unusual perspective. It was a flawed perspective on what professors do. I thought it was all teaching, and I didn't want to spend all of my career teaching. I wanted to work on some real world problems. So I went to work for IBM. And then after being there for a long time, and that was a great opportunity for me, a great learning experience, because I get to use some of my skills in many different areas. And I learned a lot. And then after 5 years, I decided I wanted a change, and so I applied for this position that was advertised at Mayo Clinic for an operations researcher. And I thought, it sounded interesting. There's no harm in applying. I didn't think I would have a chance because I really didn't have any expertise in healthcare. But I interviewed there, and they said, that's not what we need. What we need is somebody who can solve problems, and we want somebody with operations research background, and we believe you'll be able to learn some of the healthcare, because that's what they do at Mayo Clinic. And so that was really transformative for me, and that's what led me into what since then has been mainly focusing my career around using operations research and systems engineering kinds of approaches to tackle healthcare problems. And so shortly after that, I decided I did want to be a professor, because I learned that what professors do in engineering schools is actually a lot different than what I thought. And I didn't realize how entrepreneurial it could be, how much freedom there was to explore research opportunities. And once I did, then I got very excited about that. And so I went to NC State University for for my first job. That was a fantastic experience. I was surrounded by great mentors. And then the opportunity arose to go to University of Michigan later in my career, and that's a great place for me to be able to do research in medicine because we have a large health system there.
Yeah, they do, yeah.
Yeah, so that's some of the path. And then just last year I became the department chair in our department, which has been a really energizing, exciting, new opportunity where I'm learning a lot. So.
This is wonderful to when we were talking, I wrote down a few keywords, but I think the two keywords I wrote down was math and transformative. I think in your career you did have multiple, at least 2 or 3 transformative, something you don't think you will do and then you end up doing. But those are really transformative. But I think you mentioned even from your undergrad study, you mentioned your love of math. Even though it's either chemistry or physics, but I feel all those areas, especially physics, actually they have a lot of rigorous requirement of math.
Yeah.
Right,
yeah.
and then when you transform to manual science, even though they're dealing with different things, of course, I assume physics you deal with particles, and manual science you deal with people.
Yeah.
Right. So but I think some fundamental tools that you are using, this quantitative, analytical, mathematical, and also rigorous thinking. I think that's really, very consistent. And of course, when we go to IBM and we go to, Mayo Clinic, of course, this kind of very solid foundation plus, I think your passion. Right?
Yeah, I think if you get a solid foundation in what I would call critical thinking, there's all kinds of things you can do with that. And so we see that in industrial and systems engineering programs, students that go and do just a wide range of things. I mean, touching almost every industry. So it's kind of a testament to the sorts of things you can do with a degree like that.
Yeah, I think this is great. Thank you again for sharing your career path. I think that's really one of the objectives we produce these videos is also help our systems graduate students, including PhD students, to help them think about their future career. So I think your example is a great one. So, and also I through my collaboration with we have ORE here, operations research and information, and we work with people here, and I feel actually a lot of times we have a lot of domain specific problems, but when we come to the decision point, a lot of times it comes to operational research and industry because you want to optimize, right? So I think this industry engineering and also your approach is really a very nice systems approach. And also I think you mentioned your very diversified experience. I think you should be a great person for me to ask my following question, based on your experience and also, as researchers, you want to address our human beings' most critical challenges, right? So from your point of view, what do you see as some top critical systems challenges that you feel aspired or passionate to address, or at least what things do you see as key challenges?
Yeah, I think of them as challenges and opportunities. I'm somewhat biased because I've been working in healthcare for a long time.
Yeah, relevant to your research.
Yeah,
please.
so I find that a fascinating field to work in. There's endless opportunities to apply the kinds of things that we learn, and all sorts of different areas. And so I'm very excited about the opportunities that exist now to leverage massive amounts of electronic health record data that are accumulating. Most major health systems are now collecting that data. It's becoming very accessible. At University of Michigan, we have a big precision health initiative, and that initiative, part of it is making data, on our large population of patients that we see in Michigan medicine available for research purposes. Of course, with appropriate security and anonymity, and a lot goes into making sure that we guarantee that confidentiality of the data. But a lot of those challenges are close to being overcome, and so it's opening up the door to ask questions that might have already been asked but not answered. And so we have extraordinary opportunities. But at the same time, there are all kinds of methodologically interesting questions. How to deal with longitudinal data, for example, where there's a lot of missing data, which is a major source of bias. And so there are actually lots of exciting techniques that I've been learning about just in the last 5 years for ways to address and mitigate those kinds of bias so that you could develop models, stochastic models or optimization models, simulation models, any number of kinds of models that you could parameterize now with realistic data. So healthcare is an area I'm very, very personally excited about. And then as a department chair, I would say I see enormous opportunities in supply chain logistics, but also broadly in business analytics, where engineering can play and is playing a very significant role. Online retailing would be a nice example, but there are many. Another area I would say would be energy and mobility. These are two areas I think that are very exciting long-term opportunity areas, and the department here is doing an outstanding job of starting research and creating a sustainable path for using the kinds of methods that we develop for mobility problems, working with companies like Uber and Lyft. So that's very exciting to me, and we're aiming to do some similar things at University of Michigan because we think those are some of the most important long-term societal challenges that are out there. So I guess to summarize, it's sort of, to me, it's health, business, energy, mobility. These are not the only important problems, but those are the ones that I'm personally very excited about right now.
That's great, and also those are the areas seem like industrial engineer or OR can play such a significant role, especially with the abundance of data now becoming available. I think you mentioned energy and mobility, of course, Detroit, right? In the Michigan, right? That's where that's basically the empire of the cars. And I know like Amtran, I think Michigan has this Transportation Research Institute.
Yes,
right?
UMTRI is fantastic institute that actually just recently has become part of our College of Engineering.
Really?
So it's creating really exciting opportunities for people that want to work in any number of areas related to mobility, including like industrial and operations engineering, where we have more overwhelming opportunities to work in this area. Along with an industry base like you mentioned, General Motors, Ford, and a large number of companies in that space that create a nice infrastructure for people who want to do research, in that area. So.
Yeah, that's great. Because my own research is in transportation, in transportation system. Actually, my research also has to do with the other element that you care a lot is actually health. So I actually look at transportation and emissions from transportation, the air pollution, how that impact this kind of public health. So you talk about this kind of electronic health data. So I don't know how this kind of data is managed across different, for example, hospitals or something. Seems like you are working with the Michigan Health Database or something?
Yeah, we have a health system that we call Michigan Medicine. It's our university system, and a lot of data is collected into the electronic medical record, but there's a lot of other data too. Like we have a huge genetics initiative, and we have collaborations across the state where we're collecting data from smaller practices, smaller healthcare practices in rural areas, for example. So that we can also try to learn and understand some of the challenges that people face when they're in a more rural area where they don't have easy access to healthcare, like we do in Ann Arbor. So we have a great health system. It's right there in the small city. We're very fortunate, but people who have long distances to travel face different kinds of challenges. And so I think that's also an exciting problem, and it relates. It's a great example of something where there's an intersection between health and mobility, for example.
Mm-hmm. Yeah, it's a very good kind of intersection because it's interesting kind of in terms of healthcare, right? This country we spend more than 18% of the GDP for healthcare, but we have to keep in mind that healthcare is only taking care of people after people get sick. But I think we seldom ask how people get sick. Mm-hmm. Can we try to resolve the problem from the root? So, and actually that could be even more, I believe, more cost effective. Because we were awarded this U.S. Duty Center for Transportation, Environment, and Community Health. So actually we are trying to connect how transportation, how our built environment affects our health. Actually, we work with you have the Michigan medicine, and we work with Biomed Cornell, which is in New York City. They have all this historic data. They have this EHR, electronic health record data. We analyze the longitudinal data of like heart failure patient data, and after we control all the individual socioeconomic data, we find out that actually the living environment, the built environment that a person lives in, has so much to do with the progression of the heart disease patient. So like after control all those things, like how close you live nearby, a very congested road, and the PM particulate matter pollution, nitric oxide pollution, all these things have the odds ratio about 1 after we control all other things. So that's why I feel, since you mentioned mobility and you also mentioned health, I feel actually if something that can we can take a system approach, how also link mobility innovation to addressing some of our health issues. I think that would be really great. Of course, this question was totally I didn't know that you were going to talk about this mobility related kind of that sidetrack a little bit. So with these things, and I think you did mention like kind of OR research or even data analytics, how they can be applied, especially now with all these kind of electronic health data being made available to the researchers after, of course, sensitivity, measures are taken. So do you want to dive a little bit further into some kind of specific how, for example, either your own expertise or expertise from your research community can be used to address? Now let's focus on health, because I think your talk that is going about health. What kind of specific, technical methodologies or approaches that you feel like kind of these OR tools are really powerful to be combined with those
That's
data?
a great question. And there's a wide breadth. So we have a lot of faculty that work in healthcare related problems in our department at University of Michigan, and they work on many challenges. So some are working on operations management related challenges, using data from the electronic health records, but also other sources like financial claims data, data collected within hospitals. So my colleagues Amy Cohn and Mark Van Oyen are people that are looking to try to understand how do we improve the efficiency of hospitals or health systems overall in terms of patient flow, timeliness of access for patients that need to be seen. And then there's all sorts of opportunity in the area of medicine. So I have colleagues like Marielle Lavieri and Marina Eppelman who are looking at different aspects of diseases. So Marina Eppelman, for example, is looking at how to optimize radiation treatment decisions. So she studies problems where specific to people who have a tumor detected, possibly in a sensitive area like in the liver, for example. And so there's opportunities to use data that's collected from imaging to optimize how to organize the radiation program, how to fire beams of radiation in at certain angles, and even how to shape the beams so you can control the radiation exposure to the tumor while limiting, the damage that you're doing around the tumor. So you have a liver that you want to be healthy and functional, and you really just want to destroy this oddly shaped tumor. Tumors aren't round. They have strange structures. And so that's an area where without optimization and solving large-scale optimization problems and taking a really a sort of systems perspective on the goal, it's not just to harm the tumor, it's to improve the patient's life. And so not doing damage to critical organs is important. So that's one area. And then Marielle Lavieri, my colleague, also works on medicine-related problems, but looking at things like sequential decision-making. One of her projects is around ophthalmology and trying to understand how frequently and when you need to test patients that have glaucoma, and how to use not just the most recent data when you go get a test, but the accumulation of that longitudinal data over time to help infer what the next best option is. And so I see there's just many kinds of opportunities. Those are just a couple of examples, but it's a really exciting area, and you can take perspectives that are more operations, more medicine, more public health. I tell people, especially graduate students, that this is an area that you could be the leading expert from a systems engineering or an operations research perspective or an industrial engineering perspective on a particular disease. There are so many diseases, for example, and so many kinds of operations problems that nobody has even tried to touch yet. So it's wide open. And I bet in 50 years, people will say, oh, well, those people had it easy because there were so many problems and so many opportunities. And now
lucky.
Yeah, maybe we'll be lucky to have solved many of those, and there'll be new problems, I'm sure, that people focus on.
So wonderful. I think you listed several examples of specific faculty research. Yeah. They're using different approaches to address these kind of health problems. And I think it's great that because as a chair, if I'm an individual faculty, I just focus on my own risk. I don't even care, my next door is doing it right. But as a chair, I think you really have the benefit of, spending time looking to what everyone is doing here. Yeah. So now with all these, with all these different individual faculty members doing all these different specific things, now I want to elevate our discussion to another level. Kind of as a chair, you see what is the benefit and how can we bring about the benefit of systems approach? Because kind of one individual faculty is looking, for example, liver. One individual is looking at some other things. Yeah. How, at the department chair level, how do you think because you have so many talents here, would a system approach or holistic way help elevate and exploit this great time opportunity that you just mentioned? Do you have any thought on that?
Oliver, I love that question. So, because we're very sort of siloed, and that's how medicine is organized. There's cardiologists that think about the heart, right? There's nephrologists that think about the kidney. Right. What patients care about is living a long and happy and healthy life.
That's right? A whole.
Yeah.
Yes.
And so, if we were to try to use everything, bring all of medicine to bear on an individual patient, they would be spending all of their time getting blood tests. They would spend all their time getting imaging, and there'd be more harm than good. And so this is one of the big challenges, is how to connect the dots, I think. And there's a lot of exciting things too. One thing I'm very excited about is that we have a group, a human factors and ergonomics group in our department that is looking at some really key challenges around things like workplace safety and accessibility that I would argue overlap into mobility and also in healthcare. And trying to connect some of these dots even would be really exciting. I think that's where there's a potential to really move the needle towards the fundamental goal, not a sort of a surrogate goal of trying to, say, treat cancer, but to think holistically about a patient. And to me, that's would be more of a systems engineering, more in line with the idea of systems engineering, to try to think about that really big picture. So I think as a field, we're really well suited to do that. I don't know what other area would do that.
I totally agree with you, and I feel like your department, because even though all those health problems, all those health data, that have been collected by the hospitals for a long history.
Yeah.
And also, as you mentioned, because I feel those clinicians or physicians, those doctors, they are trained, I believe, more specialized than us. They're dealing with kind of your hand or your foot. You have different doctors. It's probably very hard to imagine for that community to be able to, as you said, connect those dots.
Yeah.
However, now when because industry and OR, you are really looking at these things from a holistic point of view. You are doing this optimization. You are doing this robust optimization, right? You want
and also like cognitive and physical ergonomics. We've got like a faculty member, Nadine Sarter, who looks at how do you deal with many streams of information that are coming in. You have a person who is doing something critical. Could be an anesthesiologist, for example, in a hospital who's monitoring a patient, and there's many signals. And how do you help them be able to take in that information and make good decisions without feeling totally overwhelmed or making mistakes, because we can only concentrate on so many things. We have our eyes, we have our ears. She's looking at how haptics, for example, could be used to alert people to problems, using like basically touch as another form of signal, and train people to be able to take full advantage to the extent of their capacity, cognitively, to be able to make better decisions in really critical areas. So it's something I'm very excited about, because I think there you see opportunities for linking across many different topic areas of exciting research to maybe look at more of a holistic perspective again.
Yeah, I think that I agree. It is exciting. I think it's kind of, yes, while you and me, we are now talking about this holistic approach that definitely offers us a lot of benefit. But I think at the end of the day, the bottom line is that, when we come to the specific research problems, we still need to go back, math, all those analytical, critical thinking. So I think this is probably, a time point where I would like to dive a little bit further. You talk about others' work. I want to dive a little bit further in depth of your own research.
Sure.
And
my favorite topic.
Yes. I want to let you go without talking about your own research. Of course, I don't want to peer into, because you have an exciting talk which is coming up, but I don't want to expose too much of your talk. But I don't want to ask, I think your expertise in data-driven sequential decision making. I just want kind of, for example, when you were doing your PhD research at that time, probably that word data-driven was probably not as hot as these days. But I just want to why data-driven, and what is the benefit and what is the challenge? Mm-hmm. Because now this data-driven, 20 years ago people are not talking about now, and what has made it a reality? What advantage and what technical challenges and you are trying to break?
Yeah, it's a great question. So when I did my PhD thesis, I did work on some problems where we had a sense that it's a real problem, and we made up some data that we thought would probably look like real data if you were to collect it, but it wasn't so easy to get some of these things. So I looked at scheduling problems around operating rooms. Mm-hmm. I didn't have data specifically at that time for how long, or the probability distribution for like a surgery, and how that might differ, that probability distribution across different surgeries. So we're hypothesizing things. And then later in my career, I had the opportunity to actually get that data, and that helped to inform a lot of ideas, actually, about how to change the way to look at these problems, try to better understand what the real problem is. So what I'm doing now is different. It's been a kind of a journey of changing areas and topics, something I love about being a professor with lots of freedom. And what I'm working on a lot now is thinking about how to leverage longitudinal data from electronic health records to build models of how diseases, and I focus mainly on chronic diseases, so building stochastic models of these chronic diseases that play out over long periods of time to understand how they progress over time. And my goal is to develop those kinds of models. It's not easy. Electronic health record data is observational data, so it's filled with bias.
Yes.
You know, we have data, for example, Michigan Medicine is a first-class destination academic medical center, and we have data on 10 people that tend to be sicker and have better access to care than perhaps like another population in another part of the country. So that's an example of bias. We have more data on people that are sicker than people that are healthier. That's another source of bias. And there's many of these sources of bias. And then we have issues of missing data. And missing data is actually something that can be informative. We can use that to help us. The fact that data is missing actually could carry useful information in it. And so I spend a lot of my time now learning more about techniques around statistics to build better informed stochastic models with the end goal of trying to look at how to optimize decision making over time. And so to give you a specific example, a lot of my work has been in the area of prostate cancer. This is the most common cancer among men really in the world. Many men are never detected with it, and they die without even knowing it. So it's an example of a cancer that there's multiple types. Some could be very aggressive, but many are not. And so differentiating and discriminating between those, trying to detect basically the high-risk ones early is one of the key challenges. And so we build models to understand how quickly the disease progresses so that we can decide when to use biomarkers, how frequently to use biomarkers to try to preferentially detect high-grade cancers and happily miss these low-grade cancers that have almost no chance of having a serious impact on somebody's life. And so that's an example of a sequential decision-making problem, not unlike problems you would find in perhaps like machine inspection or repair problems that people have worked on for a long time. But there are a number of differences in this case that make it exciting and also raise opportunities to develop new methods to look at these kinds of problems.
Yeah, that's true. It's kind of for my own work, and actually I also look at longitudinal data. But I look at, for example, the air pollution measurement at the same sites, over time. Yeah. Right? How that evolved. So in your work, of course, you can see that when we come to the point of treating a patient, that we're dealing with an individual. While when we are trying to make inferences, you have a sample. And especially, I think one of the strengths or this longitudinal data is that because we have this, especially now with big data, you have all this big sample size that will enable us to make better inferences by borrowing information across individuals.
Yeah.
But in the meantime, when we apply treatment to a individual patient, we have to be specific because you mentioned like precision medicine, right? Through your research, dealing with this kind of longitudinal data, I just want a little bit philosophical question. What do you see as this kind of being able to borrow information across individuals to help you with inference versus designing a treatment plan for an individual which has specific variability? What's your take on that?
This is really exciting. So this is something that I'm spending a lot of time thinking about now. How do we use large population data and figure out how to learn adequately so that we could try to make informed decisions about individual patients. And I think often what we're really trying to do is segment patients into different kinds of groups, different risk groups, for example. Getting down to the individual patient level can be challenging right now because we don't really understand enough about physiology to build a stochastic model of how, if we were talking about heart disease, how cholesterol or blood pressure would progress stochastically over time for you or for I, and how would we be different. But we could look at factors that help us to segment the population The simplest example would be men and women. We know they're very different.
Yeah.
Both have high risks and have to be concerned about heart disease and stroke. The onset for men is earlier in life than for women. It doesn't mean that women aren't at risk. It's just that onset increases and becomes more concerning later in life. And so that's one way to look at it. We also look at different ways to incorporate like random effects into statistical models. Now, how to translate that into stochastic models, I think, is an exciting opportunity area that I'm spending some time on, and I think it's a kind of a wonderful area of future research. And I'm still trying to learn how to do that.
So that's a how.
Right to the edge of like what's exciting.
Yeah, that'll keep us exciting. That you talk about this. Ask question about this data, this longitudinal data. So I think another thing you in your research is sequential decision making.
Yeah.
Right. I think that's again a very nice kind of decision philosophy. I think this reminds me like kind of if you read a lot of, especially manual science, right? When we read kind of the successful story, like if you want to succeed, either as an individual or as a company, they say that first you need to identify your goal, and then go towards that.
Yeah.
Always go towards that. So which means that kind of that philosophy is that you have a goal, you don't make sequential decision. You just because the sequential decision will allow us, a zigzag we can make.
Yeah.
So what's now, of course, for this kind of, especially this kind of medical healthcare decision, of course we are not going to be able to identify the truth immediately. We have to go through this learning process. That's why I think sequential decision making will allow us opportunity to adjust our knowledge and our decision. So what's your view about this sequential decision making versus kind of this straight decision making? What is again kind of these things kind of troubles people when you think about at a higher level philosophy from a systems level?
Yeah, so I look at it from the sort of systems and the optimization perspective, and so when I look at my perspective on sequential decision making is one of doing it under uncertainty. So we have to make decisions today without knowing exactly what's going to happen in the future. So an example would be whether to have a patient start a medication that could lower their risk of heart disease and stroke, or to wait another year, defer that decision for another year, and see what happens. Maybe their risk factors like cholesterol and blood pressure will go down. There's a great deal of uncertainty about whether they'll go up or go down, and so it's about deciding whether to act now or defer the decision. And why would you want to defer the decision? Well, the medications that are available have side effects. Not substantial side effects often, but they do have side effects. Patients tend to want to avoid them. And on the other hand, they may reduce long-term risk of an event that we're not sure will happen in the future. And so I think of it as a rolling basis. Do you want to learn more, or do you want to act now and start treatment? And then it becomes more complicated because there's half a dozen standard medications for controlling cholesterol and blood pressure. If all we cared about was extending lifespan, then we might say, well, let's just put patients on all of these medications. But that comes with side effects and harm to quality of life. And in some patients who are healthy and are able to control those risk factors, the benefits in terms of extended lifespan are extremely small versus the harms you're doing with those treatments. And so a lot of what I do is, when I think about sequential decision making, it's about, well, what are the recourse options, and how does what you would do in the future influence what you should do today?
Yes. Yeah, future decision will be dependent upon the previous path.
Absolutely.
Yes.
Yeah.
So that's great. We talk about this data and this sequential decision making, take advantage of data that keep kind of gradually becoming available to us. Now, of course, I think we did talk about take advantage of this analytical power from OR industrial engineering combined with this kind of electronic data. Of course, so far you can see that it's basically we're talking about healthcare with a combination, with the integration of advanced analytical skills plus the data. But here you can see that doctors have not come in yet. So I wanted to know about your opinion. Imagine like in the future, so now even like daily with our iPhone, some people could be collecting our health data. They can record our longitudinal data through our life. So we assuming like in the future, if data become so finely resolved and detailedly recorded in such a way, and also computer scientists and operation researchers can develop all these learning algorithms to identify what the problem is. Of course, as soon as we identify where the problem is, we can have precision medicine to do that. So which is kind of, we call it together like artificial intelligence.
Yeah.
So what's your view about artificial intelligence versus human intelligence? I mean, our traditional doctors.
Sure.
So what's the future?
Yeah, a common view is that, for people that work in the artificial intelligence area, is that optimization is part of that. People in optimization may feel that it's separate, but these things are at least highly linked to each other.
It's a core.
Core
part.
And optimization is a fundamental aspect of artificial intelligence and how you would train a deep neural network, for example.
That's right.
Or something much simpler like maximum likelihood estimation for a logistic regression model that might be a probabilistic model to help you predict a future event. So I think these things are closely linked. I definitely don't think of them as separate. I think there's extraordinary opportunities out there. So some of the work that I do, many people do, is looking at predictive modeling, which you could say falls in the machine learning realm, and trying to predict future events. And so this is something where medical doctors, they face a huge challenge because there are risk models, based on these statistical models, some quite advanced models like deep learning models, and they're bombarded with many different types of models. Heart disease is a great example. Prostate cancer is another one. All the major diseases, there are many models. And something I've gotten very excited about, and I'll talk about in my seminar, is how do you deal with all this ambiguity? Because the models, when you look at them, the same person, take all of your risk factors, Oliver, you plug them in to 2 or 3 or 4 or 5 models, and sometimes you'll see substantial discrepancies. And so why do we see that? Well, sometimes they're fit to different populations. What is it causes those differences? It could be behavior, like dietary aspects, or exercise might be different because of different cultures and in different populations. It could be a latent factor, like a gene that's not yet been discovered. So there's a lot of unknowns there, and I think that actually in itself creates a lot of opportunities for thinking about latent factor models, or I'm very excited about partially observable sequential decision-making problems where you either don't have perfect information, maybe without doing perhaps a very invasive test, and so you have to use some sort of inference to understand that, or it may be that you don't even know what that possible latent factor is, but you can see it exists because when you fit these risk models, you get very different models on different populations. And so to me that's really exciting, trying to think about that balance between sort of how to use that breadth of information, how to take it and then decide like how best to work with it.
I think that's this is probably a very good point for us to stop, because I think you made a very good point, because when you think about health and a human being, right, without the data, without today's technology, we can record a human being as a combination of different organs, whatever size, whatever scale we can go down to. However, even we record all the different behavior data of all these different organs, but we can still not explain the behavior or the health outcome. And in between, that's actually the human part, which is kind of latent variable that you are trying to use to hopefully capture so that we can link those things we can measure and those we cannot measure and try to explain what we observe.
Absolutely, and I think that's incredibly important. All kinds of research happening in the statistics community, for example, on latent variable models, but not as much as looking at, well, how would we optimize decisions, or how would we maybe take multiple models that exist and try to make use of them as best as possible. So I think there's all sorts of opportunities for us there.
So that's great. I think apparently it takes so many systems engineers who come from different source of training.
We
right?
need more. Yeah, absolutely. It's very exciting. All kinds of job opportunities. As you mentioned, healthcare is the largest industry out there. So there's just extraordinary opportunities in many areas too. I mean, I mentioned supply chain logistics, energy, mobility. And then there's many more. So it's really, I think, exciting time for students that are studying in this area of systems engineering and operations research and analytics. Couldn't be a better time. That's
wonderful. You kind of answered a question I was afraid at the time I didn't ask you, and I was going to ask what you would like to say to our future PhD in system. That's kind of you sound like you talk to them.
I think the prospects are just incredible. As maybe everybody says this at some point in their career, but I just think it's it feels like it's the best possible time to be working in this area, because so much data is becoming available. It's creating opportunities to really have an impact with the methods we've been working on, and it's also helping us understand what are some of the new problems to tackle, and maybe we thought, well, we had a certain way that we tackle these problems, but then when you start to look at the data or what's possible to collect or the problems with collecting it because of censoring or any number of challenges, then it forces you to think about how to adapt models and methods for solving those models. So it's I see it as applications driving methodology and theory, and theory and methodology driving applications. When you get people that are really good in both areas, all kinds of great things happen.
Wonderful. Thank you, Brian.
Oh, thank you very much, Oliver. It's a pleasure.
Great. Yeah, I think